Saturn, the ringed jewel of our solar system, a world that has haunted our dreams and fueled our scientific curiosity for centuries. It represents a monumental leap for humanity, the next great frontier after Mars. But here's the hard, chilling truth. When the first humans finally arrive in its orbit, they won't be coming back. Not because of some unforeseen catastrophe, and not because we can't escape its gravity. They won't return because coming home demands a ship, a refueling depot, and an entire industrial civilization in deep space that we simply don't have, yet. This isn't a failure of imagination, but a stark confrontation with the laws of physics and logistics. The tyranny of distance sets the stage for this one-way journey. Saturn is nearly 10 times farther from the Sun than Earth is. To get there with current chemical rockets without using an impossible amount of fuel, we rely on gravity assists. These are cosmic slingshots. A typical transfer weaves past Venus and then back past Earth, trading years of travel time for precious delta V, the currency of spaceflight. These launch windows open rarely, sometimes only once every couple of years. Each assist adds immense complexity and multiple potential failure points. Even the fastest, most efficient trajectories take 6 to 8 years just to arrive, and once you're there, you're truly on your own. A message sent home travels for over an hour at the speed of light. A reply takes another hour. A simple conversation becomes a 3-hour exchange of monologues. In an emergency, mission control is just a distant, delayed echo. But communication delays are nothing compared to the brutal mathematics of the rocket equation. It is a merciless and unforgiving law of nature. Every maneuver, the outbound cruise, the long burn for Saturn orbit insertion, every hop between its fascinating moons, burns fuel. But the real killer is the fuel required to escape Saturn's immense gravity well and begin the multi-year journey back to Earth. If you try to carry all that return propellant with you from the launch pad on Earth, the numbers spiral out of control. The vehicle's mass explodes exponentially. Your spacecraft becomes a colossal, barely launchable fuel tank with a tiny habitat attached. The payload, the crew and their science, becomes an insignificant fraction of the total weight. It's like trying to cross the Pacific in a rowboat while towing a fully loaded oil tanker behind you, just in case you want to row back. So, what about better engines? Multi-stage interplanetary stacks help, shedding dead weight along the way. Advanced concepts like nuclear thermal propulsion, which uses a reactor to superheat hydrogen, promise double the efficiency of the best chemical rockets. Electric propulsion, like ion drives, sips propellant for months or even years, generating a gentle but relentless thrust. These technologies are impressive, essential for making the outbound journey feasible. But none of them erase the fundamental problem: the mountain of fuel demanded for the powerful, high-thrust burn needed to break free from Saturn and get on a trajectory home in a reasonable time frame. An ion drive that takes years to spiral out of Earth orbit would take decades to spiral out of Saturn's. That's simply too long. The logical solution is to make your fuel at the destination, a concept called in situ resource utilization, or ISRU. But this introduces its own colossal challenges. The best propellants, like liquid hydrogen and oxygen, are cryogenic. Over a decade-long mission, they constantly boil off, even in the best insulated tanks. Your fuel literally evaporates into space. Nuclear power can push us outward, but that return propellant must still exist, somewhere. The most promising location is Saturn's largest moon, Titan. Its thick atmosphere and lakes of liquid methane and ethane could theoretically be refined into rocket fuel. It's an elegant concept, but in practice, it's entirely unproven. We have never landed a robotic refinery on another world, let alone one that can operate reliably in cryogenic temperatures a billion kilometers from help. There are no fuel depots, no orbital gas stations, not yet. Beyond the fuel, Saturn's environment itself is beautiful and profoundly hostile. The iconic rings are not solid. They are a blizzard of icy particles, from dust grains to mountain-sized chunks, all orbiting at tens of thousands of kilometers per hour. A collision with even a small particle would be catastrophic. Powerful radiation belts, trapped by Saturn's magnetic field, threaten to fry sensitive electronics and endanger the crew. The deep cold of space is relentless, and the long eclipses behind the planet's massive disk can last for hours, starving solar panels of essential power and forcing the ship to rely on finite battery or nuclear sources. And as we've seen, communications can vanish completely behind the planet, leaving the crew utterly alone, with minutes to an hour of terrifying silence each way. Then there's the fragile human element. A decade or more in space takes a brutal toll. Years of microgravity, or partial gravity from a spinning habitat at best, cause bone density to plummet and muscles to atrophy. It can permanently affect vision and strain the cardiovascular system, and the constant exposure to galactic cosmic rays increases cancer risk significantly. Shielding that truly helps is incredibly heavy, and as the rocket equation taught us, heavy kills missions. Every single component of the life support system, air scrubbers, water recyclers, food production, must work flawlessly for a decade or more. There's no resupply mission coming. Every spare part must be brought along, and it must be simple enough for a tired, isolated crew to install themselves. And time dilation won't save you here. At the speeds we can achieve, the clock on the ship moves at almost the same rate as the clock on Earth. While you spend years in a metal can, your friends and family age, children grow up, loved ones pass away. The entire political and cultural landscape of your home world can shift. The mission you left for might not be the one they remember. The psychological burden of this profound isolation, of knowing home is a pale blue dot you can never touch again, is immense. A one-way framing starts to look not like a failure, but like the only honest approach. Pioneers building the first permanent foothold, not visitors chasing a postcard and a quick ride home. So where would these pioneers even work once they arrive? Titan is the most practical target. Its thick atmosphere allows for aerobraking and parachute-assisted landings, saving precious fuel. The low gravity and solid, albeit cryogenic, surface make it a viable place to build a base. But even from Titan, the ascent stack required for an Earth return would be colossal, a multi-stage rocket that would have to be built and fueled on site. The other tantalizing target, Enceladus, tempts us with its subsurface ocean, vented into space through incredible plumes of water ice. But landing there is harder, and sampling those plumes means flying through them at orbital speeds, spraying the spacecraft with ice particles like a sandblaster. Operations are possible, a return journey is not. Navigation in the Saturnian system is a celestial ballet of immense precision. The flight path must thread the needle between the ring planes, shepherd moons, and the planet's shadow. Every orbital maneuver is critical. Blackouts behind Saturn cut all contact with Earth, forcing the crew and the onboard computers to have complete autonomy. A missed burn or a miscalculation doesn't just mean a small delay. It could mean the mission window for a transfer to a moon slips by months, or worse, puts the craft on a trajectory that wastes irreplaceable fuel. There are no quick turnarounds, no simple do-overs when you are operating 1 billion kilometers from home. Finally, the ethics and policy of such a mission weigh as heavily as the fuel. Worlds like Enceladus and Titan, which may harbor conditions for life, demand stringent planetary protection protocols to avoid contamination. We must be explorers, not conquerors who accidentally wipe out an alien ecosystem. And a no-return crew requires a global consensus and a profound ethical reckoning. This isn't like the voyages of early explorers who hope to return. This is a planned, permanent departure from Earth. Rescue is impossible. The contract for this crew is one of immense courage, unwavering competence, and a clear-eyed acceptance of risks that most missions would never and should never ask. So, could we ever bring them home? Yes, but only if we build the necessary scaffolding across the solar system first. This means a network of orbital propellant depots, first in Earth orbit, then beyond. It means mastering in-space assembly, building our massive interplanetary ships in orbit instead of launching them whole. It requires proving IS-RU technology, not just in theory, but with robotic missions that actually work. We need reliable, long-lasting nuclear power, both for propulsion and for powering bases. And it would all be supported by a steady cadence of slow, efficient cargo flights, pre-positioning fuel, habitats, and supplies years in advance. Until that interplanetary infrastructure exists, the first crew to Saturn are settlers by necessity, not tourists by design. We can reach Saturn. That much is within our grasp. But coming back will take technologies, infrastructure, and a sustained global commitment we have yet to muster. So the first to arrive won't be visitors returning with stories. They'll be founders, planting the first seeds of humanity in the outer solar system. Their one-way step, a sacrifice made with open eyes, will be the foundation upon which future generations build their bridge to the stars. They will be the start of a new chapter, and their journey will change everything. The stars will wait for us.